Good evening, everyone, and welcome to this Young Rail Professionals London South East Committee webinar, which is one of the first of this 2020-2021 year that we'll be hosting at the moment. So welcome. I can see a few more people are joining us now. So welcome. Young Rail Professionals, as many of you will already know, is the industry organisation for those working in the rail industry, and our mission is to promote, inspire and develop the next generation of railway talent. And this is a London South East committee, so one of the regions across the country that will be running these types of events at YRP. Next slide, please. So that's who we are, and these are some of the things we do. So we're doing networking and developing events into rail. We've got an Interrail program about how to get more people in the industry. Rail Week in October, where we promote the industry. Young Rail Tours had a successful tour to Japan earlier this year, and we also do our heritage engagement. You can find out all about this and more on our website at www.youngrailpro.com. So if you're not a member yet, then that's where you need to go after this webinar and sign up for free. Today's event is on AI, artificial intelligence, machine learning, and data in the railway. The railway can be seen as a very Victorian type of industry, which is very much far from the truth. For example, they've just announced recently, Network Rail, a new contract for what they call digital railway, ETCS, automatic signalling, and they describe it in the press releases as being replacing the Victorian signalling. But of course, as most of you already know, the signalling on the south end of the East Coast Main Line is very much from the 1980s, not the 1880s. That's not Victorian at all. There's this perception that the railways are very old and not really at the cutting edge technology, but that couldn't be further from the truth. And that's why we're delighted to bring you Ali Parandeh, who's a senior data scientist at Hack Partners, who's going to talk to you about innovation, data science in rail. And he's going to take away a really interesting workshop and presentation about artificial intelligence. So I'm going to hand over to Ali to take it away.
All right, thank you very much, Simon. Can everyone hear me? So first of all, thank you very much everyone for joining today on today's call on artificial intelligence in the railway. My name is Ali Parandeh. I'm a chartered systems engineer and Microsoft certified data scientist. I now work today as a senior data scientist for a small medium enterprise called Hack Partners. We develop rail tech products for the railway industry. And some of these technologies we use include data science technologies, such as Python programming language, pandas, and other libraries that you use to wrangle data, as well as machine learning technologies and AI in order to automate processes with such technologies for the railway industry. Now, the reason this webinar is I am trying to make it much more interesting and exciting is because we're now getting into a data-centric stage. And what that means is that we can use data to automate tasks using technologies such as AI and machine learning. And in rail industry is one of those industries that hasn't yet started using these technologies yet. Other industries such as finance, such as ad tech, and all of those industries have started using this, as well as healthcare, and they have taken quite a lot of benefits from this. And I think within the railway and transportation industry, there is still a lot of potential that could be unlocked that could take this forward to that stage. So today's presentation will be a more of an introductory presentation. We will have a practical side to the part of the workshop that you can start working with. Before we go into the presentation, what I want everyone to do is to go to this link, studioazureml.net. You should have been sent this link. This is where we go to do the practical side of the presentation, where we will learn about machine learning and how to perform machine learning on the data. So if you have not gone to this before, Simon, see if you can share the link with everyone in the chat, and so that while everyone is signing up and trying to log into this service, we can go ahead with the presentation. Also, if you have any questions and comments, please post them in the chat. We will try to answer them at the end of the presentation and before we go into the workshop, as well as at the end of the workshop, where we can get more practical experience with machine learning. One thing to note, you don't need to have any programming language, programming knowledge, knowledge of Python or anything like that. You don't have to know that at all. The software we use today is drag and drop. So you just drag and drop blobs, connect them together, configure those blobs, and press run. It's easy as that. So with that said, let's get started. So thank you very much for everyone for coming in today to the Introduction to Machine Learning with Azure ML Studio workshop. If you have ever heard of AI and machine learning before, it's such a big field. This is just a poster that one of the venture capital firms have put together of just like how big the field is. All of the startups that are coming, all of these different technologies to do with data, AI, and machine learning. And it's a massive, massive field. If you ever tried to take on a machine learning course or data science course, it could have been overwhelming because there's just so many different things to learn, and it can just make it a bit more difficult. That's why what I want to do today is just to give you the bare bones and a high-level overview of what the technology is capable to do with the data that you have at hand in your organizations. A lot of this data, nobody probably other than yourself can have access to. If you know how to use the technology, you might be able to unlock insights from this data that no one else has done before. So what is machine learning? In order to understand that, let's go back and have a look at traditional programming. In a traditional programming sense, you write a script and the computer executes that script. You use conditional statements such as if, else, switch case statements, or you use while loops such as while or for loops. If you have ever done any kind of programming in a software like MATLAB or like Excel, like doing VBA, you are familiar with these concepts. And in traditional programming concepts, you write a script and the computer executes those scripts. The computer follows the instruction and executes those scripts. With simple cases, this is fine because you write a script and computers follows that script. But for a bit more complex tasks, you cannot just write a script. To give an example, how would you classify whether an email that has come to your inbox is a spam or not spam? Would you write a script that would check for certain words? What if the scammers find a better way to go around that script? Do you keep adding conditions to that script and have like a massive nested loop or nested for if statements, just like trying to check every condition that would make you find if an email is spam or not spam? No. What you have to do is you use machine learning. And what machine learning does is that it uses data and certain algorithms to figure out the patterns in the data, such as all the data set of the emails that have been spam or not spam, and figures out the relationships within the data in order to make decisions on that. Like, for example, in the email data set, whether a certain email is a spam or not spam. And the good thing is about it is that with more data coming in and with the more the model learns, the more it can predict whether an email is scam or not scam. In other applications, it can learn from data to either automate a task, predict the future based on the historical past, or do things that represent human behavior. And it learns that using the data and the historical relationships within those data. Some of those applications that have been done today with this technology is, for example, this is just, if you go to the government website, you can see a lot of these different applications. This screenshot has been taken from the gov.uk. So for example, the ones that are related to railway here is how a signaling company used AI to help trains run on time. So they had a data set of timetables and they learned the patterns in the timetables and used that to optimize when to run trains and how to optimize those timetables. Other ways that they have used it is operational efficiency using AI, that they have used operational efficiency. And if you use it on natural text, you can, for example, classify documents, because then you can use the textual data is also a sort of data, and using algorithms, you can create models or functions that would predict based on the patterns on those data. Think of it as like doing some kind of forecasts. This is such an emerging field that has I think it's going past those emerging bit and it's getting more into a more common area. So it's like getting up top of the curve, like now down the curve of the new technologies that are coming in. And it's getting more widespread that even the UK government has started putting guidelines and frameworks together on how you need to start using this technology. So it's not even, this is like such a, it's now in a more mature state that there are not got lots of guidelines in place by the government. So to show like how this technology should be utilized in order to benefit the society the most. If it wasn't at this mature stage, there wouldn't these frameworks and guidelines would not be in place at that time. To give you some examples of how this technology has been used in the past in the railway industry, on the right-hand side, you can see a model that has been trained to see objects in videos. The model is called YOLO. You live only once. That's the name of the model. But basically, this model has been trained on lots of images, and all of those images were labeled. This is a person, this is a car, or so on. And then it used that to basically find objects in the image. Using similar technologies, an Israeli company has managed to install a camera on top of like a train, and then in order to look ahead if there are any objects on the level crossings, for example, or on the track, to give advanced warning to the driver so that they stop in time. And they can also use the same technologies to follow the track. So they can see the track, they can see like the type of signals ahead, and they can make decisions based on that. So these are like different computer vision applications. This is another example of machine learning that have been used. And this is a people counter using different types of assets, such as lifts and escalators at stations. Knowing this data, like understanding the foot counts at these assets, will help you to plan better maintenance cycles for these assets at different sites of the stations, because at the moment this is not like an automated process, and the head counting system based on sensors is not as accurate as it can be. This was just a solution we produced. I produced with like one of the hackathons I attended that just like counts people using the exactly same technology that I showed you before. Under the hood, these are just like mathematical operations that happens that helps you build a mathematical or statistical model, and then use that to make these predictions of where the object is in the image, what is that object, and I think to what level of accuracy I think that object is a person or is like a luggage or something like that. Other people have used this technology, for example, to see where luggage is. Like, for example, if there are unattended luggages in like terminals, they can use the CCTV cameras to detect those objects in those cameras. It's exactly the same technology, which is within some subfield of machine learning. So to give you a broader overview, in terms of, you may have heard different terms such as deep learning, artificial intelligence, machine learning. Where do all of those things fit? I want you to refer to this slide. So artificial intelligence is just a full broad term that encompasses everything that a computer can do that resembles human behavior. Machine learning is just a subset of that. So artificial intelligence could be anything else, could be like doing search spaces, being able to like walk around based on whatever you have learned in the past. It could involve reinforcement learning and all of those other areas of AI, which we're not going to cover today because it's such a big field. But you can see all of these different topics that are in the AI on the right-hand side. Today's focus will be mostly on machine learning. And in machine learning is basically using statistical models, statistical approaches, and data, patterns in the data to produce functions or mathematical models that you can use to predict the future, forecast, or automate tasks, or to categorize things for making decisions. So that's basically what machine learning is all about. Deep learning is a subset of machine learning that uses more advanced algorithms, such as neural networks, to do more complex tasks, such as recognizing objects in images. So images are stored in computer as a matrices of numbers. So computers don't see images the way we do. And for a computer to understand what an image is just based on a matrix of numbers, they need to do a lot of different types of operations under the hood. And neural networks allow you to map those matrices of numbers to actual labels, such as this is a dog, or this is a cat, or this is a person, or this is a luggage, in order for a computer to learn what these things are in the image. So that's where deep learning is mostly useful, for like more complex tasks that humans can do, but computers have not yet learned to do. And that's like one of the most recent advances in AI has come into place. And it's the most useful method when it comes to using camera data or CCTV data. My company uses it, for example, to detect when vegetation is about to fall on track. We're also trying to use it to see if how many people are going onto buses for head counting. It can be used in lots of different types of applications as well, depending on the application. When it comes to machine learning, though, so let's focus just on the block that this is machine learning. So let's put deep learning aside and let's put AI aside, and let's just focus on machine learning. There are two types of machine learning, two big ones. One is called the supervised learning, and one is called the unsupervised learning. In the supervised learning, your data is labeled. So in each row of your data, you say this specific date, this specific email is a spam, this specific email is not a spam, and then you just go ahead and do that for like 2,000 emails. And then you basically give that email to an algorithm, which then produces that AI model for you. And it uses, that specific type of algorithm is a supervised machine learning algorithm. If your data doesn't have those labels that this is a spam, this is not a spam, we have an unsupervised machine learning problem where your algorithm has to figure out based on just specific patterns in the data, like for example, if a specific word was used in the email or not, to categorize those emails into two categories or two clusters, whether they are a spam cluster or not spam cluster. And that is called an unsupervised learning. So when you have a label, that is called supervised. When you don't have a label, that is called an unsupervised. These different types can also be broken down into different tasks. So the supervised learning algorithms can be divided into two types of tasks, regression and classification. With regression, you're trying to predict a continuous variable, such as a house price or a taxi fare price, or for example, how much a car has, how much do these type of cars what's their fuel consumption, for example, or what is the speed that we should go at to have to be on the most optimum way of like doing our fuel consumption based on our past historical data. That's a regression problem. Classification task is the same example as I said in regards to spam detection for emails. That's a classification task. Clustering is more about segmentation and clustering data based on the patterns in it. So for example, when you go on Netflix and you watch a couple of movies, Netflix on the background uses machine learning to cluster you in different types of viewers. So if you're a horror watcher, based on your viewing habits, the machine learning algorithm will figure out if you're a horror watcher or you're a drama watcher. And then they cluster you and then they keep recommending those kind of videos to you. Same thing happens on YouTube. That's an example of a clustering algorithm. We have two other types of algorithms that we're not going to go into. Semi-supervised learning, which is a combination of these two, and a reinforcement learning, which is about, think of a robot that keeps learning about this environment, and then based on that, it gets feedback, and then based on that feedback, it learns to do things better. Such as, for example, a robot trying to go on a staircase and keeps falling, and then learns that it shouldn't go on the staircase like that, and then keeps learning from that mistake, and then keeps doing that millions of times until it's able to go up. I think OpenAI, which is an organization that does AI like in a more professional level and does research, has trained a hand robot to solve a Rubik's Cube by simulating all of those environments in a computer. So instead of like the robot learning all of those movements in a real world at real time, has managed to learn all of those things in a simulated world, run across like thousands of CPUs. So like that means thousands of operations at the same time, thousands of different environments at the same time, and learn all of those things. And now it's able to solve Rubik's Cubes in all types of conditions, when it's like water pouring on his hand, when the hand is in a glove, all sorts of things. So it's a really, really like promising like area in AI that might be like where when it comes to like putting AI in robots, that's where it can kind of go. Reinforcement learning is kind of new and it's not yet used in the industry as such, just because it's how new it is. So it generates data by itself. You don't need to give it data. The data comes from the environment. Going back to the supervised machine learning, here's an example. So if you have a bunch of images, such as cats, and you have a bunch of images such as dogs, and mixed together, when the model learns which images are cats, which images are dogs, remember these images are labeled. It can then distinguish between them whether these images are cats or not cats after it has learned them. And because the images are labeled, it gives them some kind of like option to be able to do that. And the supervised machine learning problems are divided into two types. One is a classification, where we're trying to fit a line in the data in such a way that it basically puts them into two groups, either the blue group or the red group. So with Excel, we can do this properly, but when our data is multidimensional, like we have so many different types of columns and all of these columns have relationships with each other, machine learning fits a hyperplane in all of the data points, in all of the dimensions, in such a way that these data points are basically separated out properly. In a regression problem, we're trying to fit a line across the data points. But in a machine learning problem that is a regression problem, your data points are in a multidimensional plane. So it's not even in a 2D plane or a 3D plane. You can have n number of planes, and what it does is trying to fit a hyperplane that basically goes through all of these data points, and that's what makes machine learning very, very powerful. So that's a supervised machine learning problem. Examples of the applications: let's say you have the weather data set and you want to predict what the temperature is going to be tomorrow. You use a regression algorithm to predict that, to build a model to predict that temperature. If you want to just know if it's going to be hot or cold tomorrow, you build a classification model using a classification algorithm to predict whether if tomorrow is going to be hot or it's going to be cold, whether it's tomorrow going to be rain or it's not going to be raining. So you use machine learning to do that. And lastly, on unsupervised, there are two types. So unsupervised, again, we don't have labels, so it's just a bunch of cats and dogs images. There are no labels. You give them to the algorithm builds a model, and then based on that model, based on the patterns in the data, so for example, cats has like sharp ears, or like they have like certain type of nose, it learns to categorize images into dogs or cats. So we have no labels. The algorithm learns by itself to cluster these different types of data points together. We have two types of tasks for this type of algorithms: clustering and anomaly detection. With clustering, the algorithm learns the patterns in the data and basically puts them together in different clusters, such as those viewer segmentation you see on Netflix. With anomaly detection, we have, for example, our algorithm has learned to basically check the server logs. And whenever there is like something weird in the server logs, it basically sends a flag. Like if someone tries to hack the servers and the machine learning algorithm has learned that the server is behaving abnormally, it sends a log or sends an alert to the person that something is behaving anomaly in a weird way. A good example of this could be used in railway, in, for example, maintenance tasks, when you're trying to do predictive maintenance. If you have a machine that keeps moving and it's basically producing a certain type of signal, you can basically train a machine learning model on that signal to then, if the vibration of this machine starts going out of phase or in weird areas, and the signal keeps changing, because the model has learned what the signal amplitude and frequency should be like and the signature, it then could send a signal to the maintainer that something has happened, or like this item is starting to behave abnormally. You should go and check it out. So that's where anomaly detection can be useful. So that's all we wanted to cover in terms of like the high level concepts. If you have any questions, please post them below. I will answer in a minute. For the practical side of our workshop, we will be using Azure Machine Learning Service. Unfortunately, I didn't manage to find a useful data set that we can use in the railway industry. However, the data set we're going to use is on the automobiles. So we have basically a bunch of automobiles that have been manufactured between 1990 and 2000. They have certain type of features. We're going to use this data set to basically build a regression model on the fuel consumption of these cars based on their different features. The software we're going to use is a drag and drop. You can see the workflow on the right-hand side. You just drop some blobs on the page and you connect them together. They go from top to bottom. Think of it like a river flowing down through blobs, and it processes the data that way. This is what the interface looks like. On the right-hand side, you have the area where you can click on the blobs and configure blocks. And on the left-hand side, you have your toolbox where you can find the blobs and drag and drop them into the center field. And this is your experiment area where you can connect blobs together and run the machine learning experiment. It has a really nice feature of being able to visualize data sets and being able to statistically visualize what each column does and how each column relates with each other. And they're basically a histogram of each column, so we can see how the data is distributed across, and allows us to do more basically analysis on the data before we go into building our machine learning algorithm and pipeline. And the good feature of this service is that at the end, you can deploy your model on the cloud. as a web service and get predictions in Excel. So you put your data in Excel and you send it to the cloud and get the predictions back from your model after it's trained on your data. If you have time, we will be able to show you a demo of this as well. Before we go further into the practical workshop, does anyone have any questions? I'm happy to answer them on the concepts and so on. No questions? Perfect. So with that said, Simon, does anyone have any questions?
Not just yet. So yeah, just remember everyone that you can submit questions at any time. Aha, excellent. We have one. Good stuff. Apologies if I mispronounce your name. So got a question from Navtej Sagu and asking how widespread is ML used in rail currently?
It's not widespread use at all. There are only certain startups and companies currently using it, just because the industry is not yet like aware of like different types of applications it can be applied within the railway industry. The most prominent applications are used in computer vision, where you train a model to see something, like for example using CCTV cameras. However, after you see this workshop, you will see that actually the principles and the technology can be used on any type of data set, as long as those columns within those data sets have relationships with each other, and there are some relationships in the data. You can train a model to predict something based on those relationships. And I think the reason it's not widely adopted yet is because, like, first of all, there's just like so much fluff out there about it, and it's just very hard to figure out what it does exactly. And second, it's just you need to be more creative on how you can use the tool. It's just one tool that you can use in your arsenal. Like you have other tools, you can write a script if you want, but it's just one of those tools that still is in the infancy within the industry that can be utilized. And I think Network Rail has placed some budget as well just to do machine learning projects. So it is very, very, very emergent and very, very exciting area that's still not been used, and we need more people on it to be in order to basically come up with more projects to build products that would help the railway industry using data.
Okay, great. It sounds like there's some things going on, but there's opportunity and definitely room for more. Quite a few questions are coming in. I think we maybe got time to squeeze one more in before the workshop, and then obviously I'll keep your questions here and we can ask them at the Q&A at the end. We've got some time set aside for that. Lucy Heath asks, how much data do you need to create a reliable model?
That's a very good question. So you need at least more than you need the number of rows of data you need to produce a reliable model should be in the thousands. So if you have a model if you have a data set that's only like 100 rows, 50 rows, 500 rows even, that may not be enough, and you may need to synthetically produce more data using that. So there are techniques that allow you to do that, such as synthetic minority oversampling technique, where you oversample your data. But the more data you have, the more you can build a model that predicts accurately. The algorithms that we have today are getting better and better at producing models that even use not a lot of data. But still, if one of the problems that you will face with not having a lot of data is producing accurate models that perform on all sorts of data. So when you train it on a certain type of data, it should also perform better on your test set data when you're testing it. If it doesn't, it means that it's learned to perform really well on the training data, but not perform really well on other type of data. And it's a phenomenon called overfitting. It overfits to the data set. So in order to have a reliable model, you need to have a lot of data, and we're talking about like at least 1,000 all the way to 50,000. If you have even like millions of rows, that would be really good, much better.
Okay, a couple more questions have come in, but as I said, let's hold those until the Q&A. Keep your questions coming in, pop them in the box there, and we'll get back to them once we've gone through the next section. Navtej says, so thank you very much for the answer, Ali, and good to know that NetWell are looking into this, which I agree with. So I'm going to pop off and carry on, Ali, doing some interesting stuff there.
Perfect. All right. So with that said, let's jump into the practical side. So guys, what I want you to do is go into your browsers and sign into studioazureml.net. So I can wait a few minutes for you to sign into that. So this is a tool that has been developed for Microsoft for learning machine learning. However, they have taken this further. If you ever used Microsoft Azure, there is a service now called the Machine Learning Service that you can use the Visual Designer to produce state-of-the-art models in the cloud using lots and lots of compute power. But with this specific tool that we're going to use today, just basically we're going to use it for educational purposes. So you can't do much more than like experiments with it in machine learning. If you want to do like more hardcore, like professional level machine learning, and that there is a machine learning service provided from Azure Machine Learning that provides the same interface for you to be able to use this technology. Again, you don't need to have programming knowledge or machine learning knowledge. We're going to learn some today, but it would help for you to learn those things later on as you start learning more about this technology. Because to be able to be a good machine learning engineer is to learn first a bit of data science, some Python programming, and some statistics, maths background. So I understand how these algorithms are producing these machine learning models. All right, with that said, let's go to this first phase of our practical side of workshop. You should be greeted with such an interface. Yours is probably going to be empty. I've just been doing some experiments already, so I have some items here. If you're already on the project, press on the experiment, so you come to this page. At the bottom, so the bottom placement are a bit like hidden, but at the bottom you should see a new button. When you click the new button, it opens up a pane like this one. In your own free time, you can go ahead and look at all of the different types of examples they have that they have built. So you can see how different types of machine learning are there and what they've done to build these different types of models using different data. What we're going to do today, as we're not going to do any of these ourselves, what we're going to do today, I think for your learning, we're going to try to build an experiment from scratch from nothing. So what we want you to do is I want you to create a blank experiment. When you create a blank experiment, you will be presented with such an interface. So you have on the left-hand side, you have your modules that you can open and close. I have some of mine already open. There are lots and lots of modules on the left-hand side. So yeah, just go through them on your own time. All of them have documentation that would allow you to understand how they work. On the right-hand side, you can configure the experiment, or you can configure modules when you click on a module. And the way the software works is just by dragging and dropping items onto the page. So if I, for example, I go to save the data sets, so it comes with some data sets already as samples that you can play with. If you go to the save the data sets up here and you open up samples, you can go to and drag and drop the one that says MPG data for various automobiles. So it says this data can be used to predict the fuel economy of automobiles based on various informations, such as fuel economy, miles per gallon, number of cylinders, engine displacement, horsepower, total weight, and acceleration. So take this data set and drag and drop it down here. So these data sets on the left-hand side are open data sets that you can actually grab from a website called UCI Machine Learning Repository. So UCI is a name of, I think, university, and UCI is the Center of Machine Learning and Intelligence Systems for university. And there are lots and lots of different data sets here that have been created for machine learning applications. So if you want to learn more machine learning, there are lots and lots of different problems and data sets here with the problems that you can play around with in order to help you learn different types of machine learning models and machine learning applications. The auto MPG data set where we're going to work with is this one. And it's just basically, if we look at them, if you click on the blob here at the port, you will have an option called visualize. And when we visualize it, you would be able to see what the data set looks like. So that's the data set. There are 392 rows only and 9 columns. We have a model of the car, the country code, which country it was manufactured in, the year of manufacture, so 1970s, acceleration of the car, weight of the car, horsepower, displacement of the car per gallon, cylinders, and miles per gallon. So you have all of this here. And what we're going to try to do is we're going to try to build an AI model, a machine learning model, that can predict what the miles per gallon fuel efficiency would be for given car, given a certain features, such as the ones you see on the columns on the right-hand side. So this, we're going to solve a regression problem here, which is a supervised machine learning problem. So we're going to use a supervised machine learning model and a regression algorithm to create a model that can predict a continuous variable such as MPG, miles per gallon. So given a car model and a country was manufactured in, year, acceleration, weight, horsepower, displacement, and cylinders, what is the miles per gallon in terms of the fuel consumption? And so that's what we're going to do today. We're going to try to build a model that would do that. So without further ado, let's check out the data for a bit further more. So on the right-hand side, you can see the visualization of the column. So this is called a histogram, and it shows you the distribution of the data, the frequency of the instances of each type of data. Some of these, and when you look at this, some of these are a bit imbalanced. So there are a lot of data sets between 13 and 17, and not a lot between 39 and 46. So these are like different bits of information you need to keep in mind when you want to train your model. Basically, what this means is that your model will be more sensitive to data sets around this area and less sensitive in regards to data sets around this area when you build it. So most of the predictions it will give you back, it may be around this area if your data set is unbalanced. So these are the things you can do to help improve the accuracy of the model when you build the model. You have the cylinders, displacement, and so on. One of the things we can do is we can click the MPG column and we can compare it to the other columns to see the relationships. So when you click on the MPG column, go to the compare to, so just scroll down and go to the compare to and look at the cylinder column. And you can see the relationships between MPG and cylinders. So from here, you can see that depending on different, like as you go from 10 miles per gallon to 45 miles per gallon, you could have an 8-cylinder car, 6-cylinder car at this range, or a 4-cylinder car. So so there is some relationship here that the model needs to learn in order to predict whether a car with a specific number of cylinders, what is their MPG. Same thing with displacement. There is an inverse relationship here. So some of the cars so basically some of the cars are so good that they can do, they have a high displacement and very low number of MPG, but some other cars are doing so bad that you need to spend 45 miles per gallon and in order to displace for like 100 or 150. So there is an inverse relationship between MPG and displacement of the car. If you look at horsepower, it's the same thing. The more horsepowers, some of these cars will use less MPG, and basically less horsepower. The cars that basically have a higher MPG also have less horsepower. If you look at the MPG and weight, the more weight you have, basically it reduces your how much you can get miles per gallon, and the less weight you have, the more you can get bang for your buck in terms of like how many miles you can go ahead per miles per gallon. If you look at the acceleration, it's a bit scattered around, so there is not such a there is not much correlation here. So when we have correlation, we should see a line straight from here all the way to the top. So that's, when you have a big correlation between these two columns. When it's scattered around like that, the correlation starts to diverge. So you can't see much correlation here, and you can't make much predictions based on that. So the MPG and acceleration column doesn't have much relationship between them. When you look at the MPG and year, you can see that basically it's all over the place. So again, if you have an MPG of 20, you could be in any of these years. So again, this column doesn't have much relationship with the MPG column. So we can keep it or we can discard it if you want to. Same thing with country code. If you take an MPG of 20, that MPG of 20 could relate to a car that has been built in country 1, or it can be built in country 2, or it can be built in country 3. Only the cars that have an MPG of between 10 and 15 are built in country 1, and you can know that for sure. So the relationship is there, but it's very, very loose. It's a very loose relationship. And again, if you compare the car with the model, we get a box plot which shows the distribution of the data points for each categorical column. So for each category, you get a box that shows that most of your data set is scattered within this box with the mean of this line at here. And the handlebars just show the standard deviation with outliers shown as dots. So you can see different cars have different distributions in terms of where their MPGs are at. So obviously there is definitely a relationship here. If you have an MPG of 24, you can for certainly be sure that you have a Ford Pinto car. Or if it's a Ford Pinto car that you're trying to predict the MPG on, you know for sure that your MPG should be between 26 and 20 based on the historical data that you have. So these are like some of the data analysis tasks you will do before you go into building your model. You need to figure out which columns have relationships with each other, which one of those columns you can drop. One of the things we do as data scientists is we do a dimensionality reduction, which is basically analyze which columns and figure out which columns have relationships with each other with the target column that we want to train a model on, and drop those columns that we don't need. So reduce the number of dimensions of data that would allow us to basically handle less data and basically optimize our machine learning pipeline so that it's more optimized. Another thing we do, we look for missing features and missing rows. So most of these columns have no missing values. This is a certainly clean data set. And each row of data represents an observation. Each column of data represents an attribute. That is called a standard data model that you will need before you go into producing a machine learning model. The only thing I want to bring attention to is that there are no missing values. However, there are 300 unique values and 392 rows. So that means there are 90 rows that there are actually duplicate data in here. So some of these cars have been repeated, so they may have duplicate information. So what we might have to do is basically drop, either first check if those rows are actually duplicates, and if they are, drop them before we train a model based on top of that. So just to keep things simple, we're not going to do anything yet on this data. We're just going to try to use it to build a machine learning model. The first step in order to do that, because this data set is clean, we don't need to do much on it. What we need to do is to split it into two categories. We're going to split it into a training category where we train a model on, and we're going to split it into a test category that the model has never seen, so that when we test it on the test data, we can be sure that it's performing well on the test data. And the test data should never be seen by the model, and it should never come into contact with any of the processes you do when you train the model, because otherwise the model starts learning from the test data and you're actually diluting your experiment. So in order to split the data, I think if you go to data transformation under sample and split, you have a split data column, split data module, bring it to view and connect up the data set to the split data module. And when you click on the split data module on the right-hand side, so if I click outside and I click in it, you can see that you can configure this data set. There are a bunch of options here. We're not going to go into what each ones are. If you want us, there are different types of splitting. There are different types of configurations you can put in here. If you want to know more about this module and all different types of options that are available to you, there is a link at the bottom that says more help. When you click on that, it brings you all of the documentation for all of the modules. And there is quite a lot of knowledge in here in terms of like how to build your machine learning pipeline and learning about different types of splits, such as recommender split, regular expression split, relative expression split, and so on. For the purpose of just simplicity and because we don't have enough time, I'm just going to show you how you can do that with this normal split. In here, if I just make this bigger so you can see the full set, it says the fraction of rows in the first output data set. So if you look at this here, we will be splitting. There are 2 ports, 1 and 2. In the first port, it says result data set 1. In the second port, we have results data set 2. What this means is how are we going to split it? Are we going to split it 50-50, 70-30? What are we going to do? What I want you to do is I want the 70% of the data to go to the first port and 30% of the data to the second port. We don't need a random split, and we're going to try to do a randomized split. That means that this splitter, we're going to try to take random rows of data and put them into a table and put it on the left-hand side, and then put some more random data and put it on the right-hand side. We're going to set stratified split to false. What stratified split does is that it tries to take these random data points in a way that labels are represented in the data. So if you have an unbalanced data set, that unbalanced relationship is also being carried over in the splitted data sets. If you don't do that and you just randomly take around, that unbalanced relationship, that the fact that one of your columns is unbalanced, it might be skewed, and that might give you not the correct results. Because our data set is not unbalanced as such, we don't need to do that. But for some of its applications, you might need to do that. And we're going to experiment with this as well, so we can see if it's going to improve our accuracy or not. So that's why we have it here. So let's try an experiment and see if we put it to true, is it going to make a difference or not? But before we do that, let's just make a simple experiment. Next, after we split the data, press run so that the data goes through the modules. When you press run, it then runs the module. So now when we look at the data set that has been splitted, if you look at the number of rows, how many rows did we have? About 390. Now it's 274. So that now we know that it's been splitted into 2 sections. You can also visualize the second column and see that it's been splitted. What we need to do next is we're going to try now to build a model. If you just search here for regression algorithms, if you just search regression, in the machine learning tab, it will bring you all of the regression algorithms down here. So you have like different types of regression algorithms. I'm not going to go into different details of what each are. Bayesian linear regression, from the sound of it, is a linear regression. So it's the most simplest. Decision forest regression and neural network regression are the most complex types of doing regression. They give you lots of knobs and dials to play with, and that means that you can build more complex hyperplanes that you can fit into your data to perform regression. So for the purpose of this experiment, let's just stick with a linear regression. We may not get a good performance, but let's go ahead and see what we will get. Let's change, and then what we need is we need to train. We need a module called train model. So if you just search train model here, with this module is where our training will happen. So this algorithm here, this train model is an untrained model. It needs an algorithm and it needs data. So it needs data to learn on, and it needs an algorithm to basically get trained using. So the algorithm trains the model using the data, and then the model gets trained, and then it can make predictions. So now, if you look at the port, it says trained model. But if you look at here, it says untrained model. So the algorithm trains the model using the split data. And the algorithm we're going to use is a Bayesian linear regression. The options you have on the right-hand side when you click on the Bayesian linear regression module are called hyperparameters. These are parameters that you as a data scientist or as a machine learning engineer, you play with so that you can optimize the training process in a way that the model can train better. one of the things that machine learning engineers do when they try to improve the accuracy of the models is to play around with these hyperparameters to see, based on the data they have and the relationships in the data they have, what are the best hyperparameters. Regularization just basically means which bits of data, which relationships in the data should you learn, and which bits of the relationship in the data is okay if you don't learn. It makes your model more less prone to noises in data and noises in the relationships in the data that are not very important in the task that you want to do. Those are called noises in the data. So the higher the number this is, the more your algorithm will be less sensitive in the patterns in the data. Let's keep it at 1 for now. So if you press run again, it won't run and you see the error. That means that this trained module needs something to train on, right? It doesn't know what should I get trained on. So you need to select a column to get your model trained on. So when you select a column, if you have run this experiment before, you should have these options on the left-hand side. I want you to select MPG and put it on the right-hand side. So this is the column we're going to get a model trained on. So it's going to look at the historical past data and all of those 900, all of those how many rows of data they have. And it's going to try to then learn the patterns of relationships in the data on the MPG column, so that then we can make predictions on the MPG column. Next thing we need to do is press run. And now this is the step that the model gets trained. It's going to be quite fast actually, because we don't have a lot of data sets. So now the model is trained. If you look at inside the port at the trained model, you can see that these are the parameters on the model, like relationships and like knobs and dials that the model has been trained on in a way to basically predict correctly. And what we need to do is now we need to test the model and see how good the model is performing. So in order to do that, you need a test, you need a scoring module. So search for a scar model module and drag and drop this here. So the scar module has 2 input ports. It needs a trained model and it needs a test data set. So this is why we have divided the data set into 2. So if we drag and drop the second data set in, and we drag and drop the trained model in, now we can perform tests on the model using the test data set to see if this model that we've trained is actually doing good or not. So if you now run this experiment, you should be able to get to see how your model has performed. So let's look in here and let's visualize to see how has the model performed. So these are the predictions. So you have, as you can see, instead of 9 columns now, we have 11 columns. We have 11 columns. So we now have 2 extra columns. The column on the right-hand side is basically the standard deviation from the actual, and this is the prediction of the model. So for a Ford Fairmont, the MPG is 24. The model has predicted 27. For Max GLC, the actual MPG is 34. The model has predicted 33. For Maxda, the MPG is 31, and the model has predicted 32. So it's actually doing quite well. However, not on all of them. So if you look around, you might be able to find bits that are not doing well. Like for example, this is 21, but the predicted value is 24. Or this is 38 and the predicted value is 33. So there's quite like differences in terms of like the predicted and actual. So the accuracy is not going to be that high. And the accuracy could be improved by us doing other different types of stuff. One thing could be to give it more training data. So we don't have enough training data. We only have 300 or 400 columns. If you give it more training data, then it will basically learn more. One way to do that is we could duplicate the data set. Like if we have 400 rows of data, duplicate it again and basically give it that. It just makes it very more sensitive to this specific data set. So it may not be the most advanced way of doing it if you just want to increase your algorithm. The next one is to just replace the algorithm with a better one. So a more advanced algorithm could make a model that performs much better. Before we go and do that, we need an evaluate module. So search for evaluate and drag and drop the evaluate module here and just connect up the SCAR model to the evaluate module. So what this does is that it looks at all of those data sets and aggregates them up and aggregates up how the model performed across all the rows, and it gives you one metric. So you can use that metric, such as accuracy or root mean squared error, to understand how good or bad your model has performed. So if you just run this visualization and run this experiment, because this is a regression problem, we're not going to get accuracy as such because we are predicting the actuals are a continuous variable and the predictions are a continuous variable. So all we do is we can either see how much different we are from the actual. So if we have predicted 35 and the actual is 30, there is 5 difference. But because we could be on both either on this side, we could predict 25 or 35 and the actual is 30, we could get +5 or -5. In these scenarios, when you add up the numbers, you could be 0. So that doesn't make sense. So that's why we kind of use a root mean squared error instead, where we just basically to the power of 2, the difference, and then root square it. So let's look at the evaluations and see the metrics. So we have different types of evaluations here. Negative log likelihood, mean absolute error, which is basically just the difference added up, root mean squared error, and these are all in average. Relative absolute error and relative squared error and coefficient of determination. Coefficient of determination is just basically how determinant we are in terms of like this data set correlates with the other one. But the one that we want to focus on to reduce is the root mean squared error. This is the most kind of like basic but still accurate enough metric that we can use to reduce, improve the accuracy of our model and reduce the error. So if our error is 3.3, our RMS, this is called RMS, is 3.3, what can we do now to reduce this error so that our model can predict better? If you click on the SCAR module, on the evaluate module and go to help, there are like lots of different types of metrics you can use, depending on if you have a classification task or if you have like a clustering task or you have a regression task. And like if you want to understand the differences between them, they are here. Mean absolute square error measures how close the predictions are to the actuals. Lower score is better. Root mean squared error creates a single value that summarizes the error in the model by squaring the difference that the metric disregards the difference between overprediction and underprediction. Relative absolute error is a relative absolute difference between expected and actual values. Relative because the mean difference is divided by the arithmetic mean. And RSE, it normalizes the total squared error. So it's just like basically different operations in such a way that like in certain scenarios, some of these things are more relevant for you, depending on what you're looking for to achieve. So like coefficient of determination represents the predictive power of the model as a value between 0 and 1. 0 means the model is random, explains nothing. 1 means that there is a perfect fit. So that means the model can predict perfectly 100% all of the time. However, caution should be used in interpreting auto values, as low values can be extremely normal and high values can be a suspect. And that's just because of the data, and sometimes because the model could overfit to the data. If you look at our model, it is 0.3, so it's 83% on how well the model can predict. If this is showing 1 or this is showing a very high number, you have to be a bit cautious because that means your model may have overfitted in such a way that you may need to do more tests. You may need to give it more data to understand if it's actually overfitting or not overfitting to the data. Overfitting basically means that your model has fit a hyperplane in such a complex way that it only works on this type of data. Think of it as a child that studies for an exam, but the exam questions that come is not exactly the questions that the child has memorized for the exam. So if you just memorize questions for the exam and you go and do an actual exam and the exam has actually different tests on there, different questions on there, you're not going to do well. It's the same thing with this as well. If your training data is exactly the same as your test data, your model, of course, is going to do perfectly on it because it's just memorized the patterns in the training data. And when it's gone to the test data, the patterns are exactly the same. So you can't, it's not a good measurement for accuracy and understanding how well your model has performed. So let's try another experiment. So if you see here, the evaluate module has another port. What this means is that you can actually connect up another experiment to this experiment to compare different algorithms and how they perform. To do that, what I want you to do is copy paste the, let me just turn off the movement, copy paste the score and train model. And place them here, side by side. You can put the train model here. So we're going to do exactly the same experiment, but instead of using Bayesian linear regression, we're going to try to use another algorithm that is more sophisticated. So let's try to use another machine learning algorithm. So let's search for regression, and let's search for decision forest regression. So decision forest basically creates a decision tree, but lots of this, it creates a tree of decisions. Think of if-else statements. So it creates a tree of like various conditions. If the model of the car is this, and the year is this, and the range of displacement is within this range, and this is at this category, then the MPG is this number, or at this specific number. Otherwise, it's another branch. But instead of creating just one tree, it creates lots of trees, and then it compares which one is the best, and then it uses the best one to use as your model. So your model is a tree, a decision tree in this specific model, a decision tree that predicts a continuous variable. That's why it's called a decision forest regression. Let's connect the algorithm to the train model. Let's configure the train model to look at the same MPG column, which is doing it already. And let's connect up the score model to the evaluate, and let's connect up our train and test data sets to these two modules. So the left-hand side is train, the right-hand side is test. So if we connect up the right-hand side to test and the left-hand side to the train, we now have two experiments side by side that now we can compare and see which one has performed better. A lot of things machine learning engineers do. So 70% of your time mostly is focused on cleaning data. So you spend most of your time up here just like figuring out and analyzing data sets and figuring out what needs what's relationship with what. Is the data set clean? Are there any missing values? Do I need to like parse the date times, stuff like that, parse the columns? The rest is spent on deciding which algorithm is the best algorithm and doing experiments between them to see which algorithm performs better on your data. Sometimes your data is simple and you can get away with a linear regression. Sometimes it's more complex. There are more relationships, there are more dimensions to your data, and the hyperplane, sorry, the number of axes you have in your data points, like instead of like having 2D plane, you have like multiple planes, and the hyperplane you need to fit is very complex, and it basically has a lot of bends and things like that in it. So you will need to use a more complex algorithm that considers a lot of different things in order to fit a model to the data. A decision forest does that, and you can see on the right hand side you have way more hyperparameters compared to linear regression. And if you want to know more about this specific type of algorithm, again, there is a link down here that you can click and go there, and it has two different types, and it just goes into how many decision trees do you want to create, maximum depth of the decision trees, how many steps do we go deep, number of random splits per node, how many branches should each node be able to have. The more branches, obviously, the more patterns you can learn, and the deeper you go, the more patterns you can learn. Obviously, the more patterns you can learn, the higher the chance that you can overfit your model to the data. So you have the same problem as the child memorizing for an exam and then performing bad on an exam. So it's a trade-off. It's an art and science at the same time, what numbers you should have. So it comes with some experiments on like in terms of the data sets you have, what are the best numbers and what are the best parameters to use. Obviously, there is, because still AI is advancing, there are actually AI models that has learned to improve AI models. Basically means we have now AI models that can predict which one of these are the best. So we actually have AI models training AI, getting better at training AI models. It's just become more meta. It is called Auto AI. all you have to do is you supply the model, and it just basically trains everything up. It figures out which algorithm to use. It automatically tunes all of them. It gets rid of all of the dimensions. There are actually now AI models that does that. IBM has done one, so I can show you in a separate call. If you contact me on LinkedIn, I can show you an example of that. But for this specific scenario, let's just run this experiment and let's look at the evaluated results to see which algorithm has performed better. Remember, we're going to look at the RMS, root mean squared error, as our measure to see how our algorithm has done better. So we're just going to wait for this model to train for a bit, and then we're going to show you how our algorithm has behaved so far. Perfect. So now, if you look at the evaluate module and visualize that, you see that we now have two results. The first result is our linear regression at 3.3. The second one is a more complex algorithm that we have used, is now at 3.1. So it has performed much, much better compared to the other algorithm. Again, lower negative log likelihood, and all the others are kind of lower as well to some extent. And we have a higher coefficient of determination at 85%, just by switching off the algorithm. We did that and nothing else. Obviously, we can go ahead and experiment more with the data, and we can tune the hyperparameters. We can even have another module that would tune this module by the hyperparameters. So if you go, for example, go to parameter range, you could basically use sliders here to set a range of hyperparameters you want to use. And then you can have another module that would play around with these numbers to figure out what are the best numbers to use in order to build a better model using this algorithm so that your RMS can drop. I will basically leave that to you to figure out how you can do that. The model you need to use is called tune hyperparameters. So you can drag and drop this in here. Free inputs, there's a lot to this specific module. For your homework, or if you want to learn this more, try to see if you can tune the hyperparameters of this decision forest algorithm using this module, which allows you to get much, much better accuracy in your data. If you click on here, you should, if you click on the properties and you go to more help, you should learn, there is some instructions on how we can connect this up and how we can configure it so that you get much better accuracy when it comes to evaluating your module at the bottom. In the interest of time, I'm not going to do that. I'm going to just basically delete this module, and I'm just going to show you a demo on how we can use this trained module now. So let's say the model that we have trained that we want is this one, is this decision forest one. It's performed better. What we're going to do is we're going to run it just one more time because we played around with the settings. We're going to run it one more time so that we can get our final model. So here we've done our evaluations, everything is good. The accuracy we have is 85%, correlation, the coefficient of determination, and the RMS is at 2.9, not bad. If we look at the, let's just finish running. If we just look at the data set down here, you can see that the numbers are getting closer and closer. So 32, 31, 21, 17 is not that bad. There are some still mistakes, but not that bad. 14, 18, 24, 24, 35, 30, 27, 27, 27, 17, 19. So it's not that bad. There are still some mistakes. But let's say for the sake of experiment, we're happy with this. When you click on the model, you can then set up a service, a web service that you can get predictions from. So you can deploy this model on the cloud and you can get predictions from it. So select the model you have trained, which is this one, and press predictive web service. Just a second. So this creates separate modules for you. Basically what these mean is that the web service that it has set up, these modules, is whenever you send a request to the cloud, the request comes from this module, goes to the split data, and then gets split up it's sent down through these pathways, and then your model then sends an output, and then you use that output here. So this is basically what the new modules that came in mean. So you can see how complicated this can get, and then you can use this as a way of your experiments to go forward. So I'm just going to delete this so we can keep this more simple, and then go from there. So that's it for today. Does anyone have any questions that I can answer going forward? Thank you very much as well all for listening to this stage. I hope it was useful for you.
Thank you very much. A very comprehensive run through, perhaps a little bit too comprehensive for some of the functions of the modeling software that you've been showing us today there, Ali. So thank you very much for going through that. Yeah, just a bit of time for some more questions that have come in. So although conscious of time, almost at dinner time, let's see, where was he? So one question that came in from Daniel Oshinyemi is, in reality, would you use a combination of unsupervised and supervised machine learning?
In reality, basically one of the things you have to do is you first have to define what the problem is. If it's a classification problem or regression problem, it's a supervised problem. If you don't have labels, then it's probably an unsupervised problem. Sometimes, even if you have an unsupervised problem, and you train a model on it, it's not still performant enough, it's not good enough, then in that case, you will have to convert that problem into a supervised problem. That means you have to go and sit down and label your data by one. In the semi-supervised problem, you label some of the data, then you train a model on that data, and then the model itself labels the rest. And then you can then use a supervised machine learning algorithm on top, which makes your life much easier. So you can still automate the process to some extent. Does that answer your question?
I hope that answers Daniel's question. You can of course type in the chat box if it does. It does, thank you, he says, which is great. And Rory Cook submitted a question which was, are other countries further ahead in incorporating machine learning into rail systems, or is the UK forging ahead and competing in that space?
So I would say some other countries like Israel, for example, are already a bit ahead in terms of some of their startups that have started doing this. In the UK, I would say that this is something that's still emerging. A lot of consultancies are now looking into it. I know, for example, that Atkins has started using ML to predict, to basically detect whether there are cracks in the rail tracks. So you just basically keep looking at the tracks, and then when there are some cracks in the rail track, they have trained a model that would detect that. So that's something that they have done. We're doing quite a lot on using machine learning and computer vision as well, doing that. We're using the same kind of technologies, not specifically machine learning, but for example, Python, pandas, and data science technologies to extract insights from data to reduce train delays in the rail network. So using signaling data and train movement data, combining them together in order to produce visualizations and insights for our client, so that they would be able to operate the railway much better. But I would say in other countries, they are also still experimenting, but the whole industry as a general, across all the different countries, they still haven't used this technology as much as they could.
Okay, that's great. And he really liked the presentation and says many thanks as well. So yeah, I think there's a couple of other questions we could run through just before we really eat into people's dinner time. And one thing I was wondering was, in just following on from the previous question in a way, was are we fully aware of all the different aspects that AI and machine learning can play a role in terms of the rail industry? You mentioned one thing in terms of infrastructure assessment on the condition of rails, service optimization, for timetabling, I think was the other one you mentioned. Are there any other spaces that, particularly ones that you might not think could be used by AI, but actually are amenable to it?
So one of the examples that I used AI in that was actually quite novel was maintenance reports of lifts and escalators at stations. One of the problems that they have is that maintainers, when they go and maintain these lifts and escalators at stations, they write a textual report, like it could be 2 or 3 paragraphs long. And then they basically submit that in a system that gets logged somewhere. And when you look at it, there are 125,000 reports. And sifting through that, and you're trying to identify what are the causes of lift breakdowns or escalator breakdowns. As a human being, this is impossible. It takes a lot of effort and time, but with AI models, this is actually quite a swift experiment. All you have to do is label the data for some of the bits. The model can learn some of those areas. It can read some of the text and learn based on the labels what each problem is. And then it can go ahead and basically classify all the different reports. Then you can basically aggregate that labels, and you can generate insights and understand, for example, what are the causes of breakdowns. And specifically, if you have entrapments, you can use the same technique, NLP, to understand if you have entrapments in your lifts, then you can filter the data set by entrapments, and then you can use the same technique to figure out what are the causes of entrapments. And you use AI to do that, but this is like an application that no one thought, like when can we use NLP like in railway? Like there is no textual data set in railway. We mostly use like numbers and categorical data and stuff like that. But actually, it depends on what data sets you have. And the problem is railway industry, lots of data sets are private. They're not open compared to other industries such as like, for example, healthcare, finance, and things like that. In finance, they've used it a lot. Like they've used NLP quite a lot. Whenever you go to websites that there are chatbots that like talk to you and like process your applications, like even NatWest and stuff, they have chatbots. Those are all NLP applications that they have basically trained on customer data. They have lots of data from customers that they can train on. In railway, we don't have lots of data, or if we do, it's not there yet. I mean, we haven't used it there. It's just sitting somewhere in a database. I guess one of the things that would be more emerging is when we try to combine IoT with AI. That means we have sensors logging data from the railway assets. These sensors feed the data through the cloud to the AI models. AI models get learned in batches in like certain times, like midnights at 2 p.m., run all the data through the model to train the model, and then put it live again so that the model keeps predicting and stuff. So like these are like some of the applications that no one has yet done that we can start doing to make make experiments and start using the technology much further.
And I suppose going on from that, there's this narrative in the media and in general society about the idea that that AI will replace jobs, but there must be, where do you see that? Where do you see that going? I mean, I suppose it's a case of, there are certain things we can automate, particularly if we have lots of data, but then we need people coming into the industry who are able to understand, handle, process, and use that data correctly.
Yeah. So at the moment, the state of AI is not there that it can completely replace humans. At the moment, whenever you create a model, even if it's like doing really well, like something much, much better than a human being, it's a very, very, very specific tasks that you can do quite well. Like, for example, classifying images. Like humans can do that. You can classify between dogs and cats, but basically it can do that. Like it can tell you the breeds of dogs and cats. For human beings, you need to sit down and learn all of those breeds before you can do that. So this very, very specific type of tasks that AI models can do. So it's still a very long way from like AI replacing human, like human workers. My view is that with the creation of like those AI, like as AI gets more advanced, there are also creation of more jobs in the industry on AI. So for example, it wouldn't be a complete replacement of human beings. It would be human beings assisted by AI. So imagine you, for example, if you're working in a factory, instead of like doing most of the boring repetitive tasks of like doing assembly line, you have an AI model that keeps assembling to doing the assembly line, but you supervise the AI model and you keep retraining it and training it and managing it and figure out ways to like improve the process and like come up with ideas on how to do stuff better. So instead of like doing all the mundane tasks, or actually your mundane tasks that are going to be replaced by AI doing all the mundane tasks, and your tasks are going to become more interesting. So jobs change and new jobs come into play, but the old jobs, there are very few of them that might get completely replaced by AI, and we are very far from that. So I don't see that happening anytime soon.
Okay, that's great. and I suppose a relief. We're not going to be taken over all by computers, which is great. We'll be using them to make things better, which I suppose is the idea. So thank you very much for your presentation, Ali. It's been really interesting and engaging, and I've had a lot of great feedback from it. Is it possible you could pop onto the last slide in the presentation, Ali?
Yeah.
Cool. So if you want to run through it again or find out more information about YRP, just here's some info on the slide. So the webinar has been recorded, so it means you can go over it again at your leisure, and all of our webinars are being uploaded. We have a YouTube channel, which is where they're going, and you could just search Young Rail Professionals. You'll find the channel, and you'll see this webinar uploaded in there, which will be down there shortly. Also, if you want to become a member and sign up or find out more, then do get onto our website, which you can see the address is there. And here's a summary of the upcoming events, one of which is tomorrow. West Midlands Region's hosting, again, another topical subject here in collaboration with Women in Rail, as it is International Women Engineering Day. That's pretty appropriate. Andrew Haynes, NetRail Chief Executive, is addressing YRP members on the 30th of June. And we've got Human Factors and Rail, which is when you'll see myself again chairing that event, looking at human factors. And then there's a week after that, Disrupting Disruption as well. And if you want to find out more and sign up for these events and these webinars, then do go onto our website. So thank you very much to Ali. Check out Hack Partners. It's doing some really interesting, amazing stuff. And we hope you have found this webinar engaging, interesting, entertaining, and a bit more interactive than the normal kind of sitting and staring at a computer screen. Well, you're still sitting and staring at it, but you're obviously fiddling around with things, which is sometimes a bit more interesting. So thank you everyone for attending. I hope you enjoyed it, and we look forward to seeing you at the next region's webinars and at our next one as well. So thank you all for attending.
Yeah, thank you very much, everyone. Thanks, YRP.